All right. Thank you so much for inviting me to this event. Very excited to be here. And for those who don't know me, my name is Stefano. I've been a professor of computer science at Stanford for about 10 years, leading a research group focusing mostly on generative models, what's now known as generative AI. And my group is mostly probably known for the early work that we did on diffusion models. We kind of like developed some of the very early models back in 2019, where the field of image generation was kind of like dominated by generative adversarial networks. We came up with this alternative approach, what's now known as a diffusion model, that was achieving much better results. And since then, I've been trying to get diffusion models to work on not just on image generation, video generation, but also on language and code generation. So getting diffusion models to be able to generate a more discrete kind of objects. And that's kind of like the topic of the discussion today. I wanted to share some of the research I've been involved in trying to get diffusion models to be competitive with autoregressive models, not just for image, video, continuous modalities, but also for discrete objects. So to give you a bit of background, you probably all are very familiar with all the excitement that there is today around generative AI solutions. Again, I've been working in this space for a long time, probably almost a decade. I still remember back in 2014, where we were working on building little generative models that could create images for MNIST and very low resolution, kind of like black and white images, very, very poor kind of results. And it was even hard to write papers about this topic. You had to, the papers were getting rejected because people would not kind of understand why would you ever want to build a generative model. It kind of like didn't make sense, and we had to motivate the research and the papers by telling these stories about how one day using generative models we'll be able to learn features in an unsupervised way from unlabeled data, and that will help us do supervised learning, which was what people cared about back in the day. But obviously, since then, the field has made an enormous amount of progress. Like, it's almost unbelievable the kind of results we are able to achieve with existing generative AI models. We have models that can create beautiful images, just starting from captions. We have models that can convert sketches, the kind of sketches I could create, like the one you see there on the left, into, again, beautiful images, kind of like enabling people to express themselves as artists. Obviously, video generation is extremely exciting. We have systems that can create videos on demand just based on prompts, like you see there from a model that was, I think that's from Sora from OpenAI, one of the state-of-the-art models. And then, of course, lots of excitement around chatbots, text and code generation. We've heard in many of the previous talks were focused around LLMs and the capabilities that are enabled by these systems that can create text, that can write code for us, agents. Lots of excitement around the progress that we've seen in language and text and code generation. Now, when you think about the state of the space, it's kind of interesting because there's kind of like two main types of generative models that exist today. When you think about continuous modalities like images, video, even music, all the best models, the state-of-the-art models that are out there are based on diffusion. This is the kind of approach that I mentioned today, something very close to my heart, where you're kind of like generating the content by some kind of iterative refinement process, where you start from noise and then you gradually refine it until you get the final image or the final video. On the other hand, if you think about text and code generation, for example, LLMs, ChatGPT, Gemini, Claude, they're all based on autoregressive approaches, where you're kind of like generating left to right, one token at a time. And so as a researcher, this is pretty exciting, right? Because it kind of like begs the question, what's the best model? Like, why aren't we using autoregressive models for image generation? Or why aren't we using diffusion models for text generation? What's the best approach? Like, is there a better kind of like statistical model that we can use to eventually build the best generative AI solution, right? Kind of like probably a lot of people would agree that generative models seem like a pretty reasonable path towards human level intelligence. Perhaps you buy into the Richard Feynman quote about, what I cannot create, I do not understand. Is sort of like this idea that in order to be able to really understand the meaning of a concept, what it means, what's an apple, or what it means to understand Korean, for example, you need to be able to generate. You need to be able to draw an apple. You need to be able to speak Korean. And so it's pretty clear that generative AI is a super important technology, but at the core of generative AI, we're just building statistical models. And so as a researcher, it's pretty exciting that there is this dichotomy where there's two types of generative models that we use today, and one is good for continuous data, one is good for discrete data. What's the optimal approach for building a generative model? And so again, kind of like if you think about at the highest possible level, there is autoregressive models, which at a very high level, they work by generating content one element at a time. So if you think about image generation, they might generate an image pixel by pixel, left to right, like you see there. Or if you think about text, they might generate text one word at a time, one token at a time. And on the other hand, if you think about continuous modalities, you have diffusion models that they work like this beautiful image of an astronaut riding a horse that you see there on the top right, where the image is generated all at once by refining the object. You start with pure noise, and then you gradually see the image appearing. Very different kind of generative process. And it's interesting that one approach is better, state of the art for images, video, music. The other approach, autoregressive models, is currently the most widely used for text and code generation. And I've been doing a lot of research, basically dating back from the very first diffusion models that we were able to build on image generation, trying to see, is there a way to get diffusion models to work also for text and code generation? And that's going to be the main topic of this talk. I'll try to convince you that perhaps there is a change coming, and diffusion models, when they're built in the right way, when they're trained in the right way, they can be competitive with autoregressive models. And I can see a future where all future large language models are no longer going to be based on autoregressive modeling, where you generate slowly one token at a time, but instead they're going to be generating answers, answering questions for us, writing code for us, using a diffusion approach, kind of like you see there at the bottom right, where you kind of like start with the whole answer and then you iteratively refine it until you get the right solution. So to dive a little bit right in, pretty much all or most of the existing large language models are based on the autoregressive paradigm. And it's a very simple kind of like approach where you're essentially reducing generative modeling to something we understand, which is basically just discriminative modeling, supervised learning. So all you have to do if you want to be able to generate, let's say, text, is to train a neural network that can predict what is the next word going to be. And if you can do a pretty good job training this kind of model, you can train a neural network to predict the next word reasonably accurately. And again, this is, at the end of the day, a standard classification kind of problem. Then what you can do is you can generate answers to questions, or you can write code. You can do a lot of interesting things just by basically sequentially predicting words in a left or right way, one word at a time. And so let's say you start with a prefix like once upon, and then you get the trained LLM, this classification model, to predict what is the next word, and maybe we'll predict A. And then what you do is you just take this prediction, you feed it into your context, and you get the neural network to predict what is the next word after once upon A, and then maybe we'll predict time. Then you get this new word, you feed it again into the context, and you predict the next one. And so you get once upon a time there, and you keep going. And that is, at the end of the day, the whole idea behind existing large language models, next token prediction, and you just sequentially enroll them at the inference time to get answers to your questions. That's very, very simple. It's probably the simplest kind of generative model you can think of. And it's nice because it's just reducing generative modeling to classification, which is something we understand. It's something we had a lot of success using deep learning. It's just training large neural networks to do increasingly well on various kinds of prediction tasks. In theory, it's actually a very flexible kind of like formulation, although it might seem like it's pretty restrictive to generate based on this approach, one word at a time. In theory, just because of the chain rule of probability, any joint probability distribution can be factorized into a product of conditionals. And so to the extent that you have very, very flexible, very, very powerful neural networks, this approach can, in theory, represent any kind of probability distributions, including very complex ones. And it's also like, if you think about the way ChatGPT generate answers to your questions, it's a pretty reasonable kind of like inductive bias. If you think about how we write text, we tend to write, again, kind of like left to right. Perhaps, there is a little bit of iteration. If I'm writing a paper, if I'm writing a document, maybe you start with bullets and then you refine them. But the idea of generating left to right, it's kind of reasonable. And perhaps that's one of the reasons these models actually work so well for text generation, code generation, all the kind of exciting applications that we've seen also in previous talks. Now, if you think about the downsides, it's also a pretty simple kind of like approach where a lot of things could go wrong. Perhaps the most famous one is this idea of sampling drifts or compounding errors. Jan LeCun is known to be a critic of this autoregressive paradigm. He's said publicly multiple times that he doesn't believe that this will get us to human-level intelligence and that this approach is fundamentally flawed. And the basic idea, the basic problem, very intuitively, is that you're feeding your own predictions into the model. And so, realistically, your model is never going to be perfect. It's going to make mistakes. And then you're going to feed these wrong predictions into your context. And the data that the model is seeing starts to look more and more different compared to the ones it's been trained on, because there are these mistakes that have been introduced by the LLM itself. So eventually these errors compound, and eventually you're going to get the wrong answer. And that's kind of like a very sort of like old type argument that people have been using for a long time, even in the context of dating back to the 90s, where people were building the first prototypes of self-driving cars. This kind of approach, which in that context is known as behavioral cloning, is known to have these sort of issues, and that it's very hard to get it to work in many other contexts other than language, where we've seen that the results are actually reasonably good. It's also not a particularly reasonable inductive bias, this left to right generation for non-language tasks. Like if you think about generating images, there's no natural order. You wouldn't generate an image pixel by pixel. The way you draw an image is quite different. And similarly, if you think about DNA, other kinds of modalities, they don't have this kind of like left to right inductive bias. It's also kind of like forcing you to use a pretty constrained kind of architecture where you're only allowed to use the context to the left to generate what comes after you, which is potentially pretty restrictive, because we would like our models to be able to use all the information and be able to use information to the left and to the right as they make edits. So in practice, this is forcing you to choose certain kinds of constrained architectures and limit the kind of neural networks you can use to solve the kind of prediction problems that you need in order to generate text. And perhaps the biggest limitation is that it's very, very slow. This kind of, if you think about the way generation works, it's very sequential. You're effectively, it's a for loop, effectively, where you need to generate one word at a time, and you cannot generate the 10th word until you generate everything that comes before it. And so this kind of generative approach, it's extremely sequential, and it does not map well to parallel compute, to GPUs, where we would like to be able to process many different things in parallel. You have a very kind of sequential type of dependency graph that does not enable a lot of parallelism that we would like to use in order to make these LLMs even faster, even cheaper to serve at scale. Now, the alternative approach, the one that is very close to my heart and works best for image, video, and music generation, is based on diffusion. It's a very different kind of generative procedure where in order to define it, the best way to think about it is to think about not the process of generating data, but the process of destroying structure in the data. And so you can imagine a process where we start with, let's say, images, like the one you see here on at the bottom left, and then we slowly destroy the structure in the images by adding noise to the images. And if you keep adding noise and adding noise and adding noise, eventually you have destroyed completely the structure in the data, and you're going to be left with something that is pure noise. And so even in this kind of like little heat map that I have there at the top of the slide, you can see how a multimodal, bimodal distribution P0 is slowly converted into a single simple Gaussian distribution by adding noise through this diffusion process. I'm not going to go into the math, but the critical thing to think about is that if we somehow were able to flip the time axis and go from noise to data, then we would have solved the generative modeling problem, right? If we somehow can flip the direction of time and we can go from noise to data, then we have built a system that can generate images for us, that can generate videos for us, that can generate music for us. And this is the core idea behind diffusion models. This is how diffusion models work. At a very high level, again, there is still a neural network involved, but the neural network is not trained to predict what is the next token, what is the next pixel. The neural network is trained to remove noise. So you train the network to take a noisy image, let's say for image generation, and try to figure out how should I remove noise, how should I clean it, how should I produce a clean image corresponding to this, let's say, noisy dog. And again, this is something that you can do at scale. You don't need any labels. You can just take very large amounts of unlabeled data. You just add noise to the images and you train the model to remove the noise. Now, how do you use this model at inference time? Well, the basic idea is that you can start from pure noise, and then you can gradually use this trained model that you have to fix mistakes, remove noise until you have a clean image. So you can start from pure noise, and then you slowly remove noise. You gradually refine the image using this neural network that you've trained until you get your clean sample at the end. And this is the approach that is originally came out from my lab in 2019. Then it was later picked up by a lot of industry players, Midjourney, Stability AI, the Sora models, VO, Imagen. They're all based on this core idea. And this makes sense because diffusion models have a lot of advantages. The network that is trained to remove noise can have any neural net. Basically, there's no constraint on the kind of neural network architecture you can use. You can use context to the left and to the right as you remove noise. There's literally no constraint. You don't need any causality. You don't need any causal attention masks. You can use any neural network you want. You're able to use all of the context to figure out how to solve this denoising task. Training and inference are decoupled. So as you think about sampling from these models, at the end of the day, what you need to do is you need to solve an ordinary differential equation or stochastic differential equation. And so it's possible to use numerical techniques and discretize time in clever ways so that you can generate from these models really, really quickly, like instantaneously sometimes. You can also trade off quality for speed. After you've trained the model, you can decide basically how much compute you're going to use at the inference time to control how much you care about quality versus how much you care about speed. Turns out the models tend to be more data efficient. They tend to be a little bit smaller compared to the kind of like massive autoregressive models that people usually train on text and code. They support controllable generation. I'm not going to go too much into the details, but the idea is that because you're working with the full object to begin with, it's actually a lot easier to steer a diffusion model in a certain direction So if you care about, you have certain constraints that you need to enforce on the output, or you have some other kind of reward function that you want to use to kind of like bias the generative procedure in a certain way, it's very, very easy to incorporate these constraints in a diffusion model, because you know from the very beginning what does the object look like, and you can kind of like push the denoising process in a direction that will also, let's say, satisfy some kind of constraint that you have over the outputs. And it also has this nice kind of like inductive bias where the model is trained to fix mistakes, and then at the inference time, it's used to correct mistakes, which is quite different from an autoregressive model where once you output something, you can never take it back. A diffusion model is actually trained to fix mistakes, and so it could be potentially more robust to mistakes that are introduced by the fact that it will never have a perfect denoiser, as we will never have a perfect model that can predict the next token. So what are the downsides? Well, it's been hard, very, very hard to get diffusion models to work on discrete data. And the reason is that if you think about diffusion, that's a very continuous kind of process. It involves stochastic differential equations or partial differential equations, the Fokker-Planck equation. Kind of like involves this idea of taking an image and adding noise. There's a lot of geometry that you kind of like need to have in order to build a diffusion model. You need gradients, you need calculus, stuff that does not necessarily have an equivalence in the discrete world where you're thinking about text. Like, what does it mean to take a word and add noise to it, right? It's less clear. Or what does it mean to interpolate between two words? There is not necessarily an obvious counterpart. So in order to define a diffusion model for let's say, text generation, we can try to follow the same kind of argument. First, we can define a process that we can use to destroy structure in the data. And this is a process that essentially will add noise to the data. And there is several ways to do it. One way would be to just randomly delete words. Instead of adding noise, we can randomly delete words. You keep deleting words, eventually you completely destroy the structure in the data. There's no information left. You cannot make sense of the original sentence if you keep masking out words from that sentence. And another possible process that you could use to, again, kind of like corrupt the sentence is to randomly swap some of the words. So you can start, where are we going? And then maybe you take the first and the third word, and then you swap them. You swap where with computer, and you swap we with moon, and you end up with something computer, are moon going, which makes less sense. And if you keep swapping more and more words, again, you kind of like destroy the structure and you're left with something that has no meaning. Now, once we have this process that can gradually kind of like take data and destroy it by removing all the information, by adding noise in a suitable way, we can train a model to reverse this process, just like what we did in the context of image generation. We can try to train a model to correct these mistakes. Let's say, take a sentence where some of the words have been masked out and predict all the missing words. Or you can take a sentence where some of the words have been flipped, maybe you don't know which ones, and the model has to fix the mistakes, has to correct the sentence by, again, fixing the words that have been flipped. And if you can train such a model, then again, we can use the same idea that we had before, this idea of start with pure noise, and then just get the model to keep fixing mistakes, keep refining the output until you get a clean answer. And so it might look something like this. You start with random words, and then you keep fixing them until you end up with something like, running is great for your health, right? Similar to pure noise data. Or, if you have masks, then you can kind of like start with pure mask, and then you get the model to infill some of the words until eventually you have a full sentence that actually makes sense, like running is great for your health. Now, it turns out that this approach actually works really, really well. So if you train the neural network in the right way and you define a suitable continuous time process, which is kind of like a diffusion over a graph, you can use a lot of the ideas that worked well for diffusion models, and you can translate them to text generation. So we had a paper last year where we introduced a method called SAIF, a score entropy discrete diffusion model, which is actually really exciting because for the first time, we were able to match the quality of an autoregressive model at the GPT-2 scale, so at relatively small scales. We were able to train a diffusion language model that was able to match and in some way surpass the capabilities of an autoregressive models of similar size trained on the same data. Kind of like highlighting that maybe diffusion models could be a better approach if they are scaled up in the right way. And this plot here on the left is perhaps the most exciting kind of result. And what this plot is showing is it's showing the quality of the samples that you get using this diffusion approach, this refinement approach, as a function of the number of denoising steps that you do. Like how many times are you going to call your neural network to remove noise to clean up your sample? And the more denoising steps you do, the higher the quality. So on this graph, you want to be as low as possible. So generative perplexity is a metric of sample quality. So you want to be as low as possible. And as you can see, kind of like at two different sizes, GPT-2 small and medium, you can see that kind of like the quality keeps improving as you increase the number of denoising steps. But what's exciting is that the quality is the stars here. The stars basically correspond to an autoregressive model with the same number of parameters trained on the same data. And in order to generate 1,024 samples with one of these autoregressive models, you need 1,024 neural network evaluations. So you need to sequentially go and generate all the tokens, which can be very, very slow. And what's exciting is that with that diffusion model, we're able to essentially match the quality of what you would get with an autoregressive model run for 1,024 steps using far fewer denoising steps. And this is exciting because you can kind of think of the number of denoising steps as the amount of compute that you use or the wall clock time, essentially, that you need in order to generate a sample. And so this was very, very exciting for me. It was for the first time we were able to kind of like match the quality of an autoregressive model at a relatively small scale. But that really got me excited, and that and a few other results kind of like show that indeed it can compress the data really, really well. And it got me excited about this technology. And so I've been working towards scaling these models up. So I started a company called Inception AI, where we've been scaling up diffusion language models. We've turned the first commercial scale diffusion language models. And what we've seen is that these trends indeed continue to hold as we increase the model size and as we improve the quality of the data, and we do all the tricks that you would need in order to get a high quality language model at the end. And here you can see a little demo of how the model works for text generation, or code generation. You can see on the right that if you ask the model to generate a function for LLM inference, you can see that this diffusion approach, where you iteratively refine the full object, doesn't take a whole lot of iterations to complete, and it can be, in this case, 5 times faster than what you would get if you were to go through every single token in an autoregressive way. And what we've seen is that these diffusion language models are really high quality. So they are comparable in quality with some of the best models out there, including speed optimized models from frontier labs like Anthropic and OpenAI. And they are significantly faster, like 5-10x faster than autoregressive models of similar quality. And so in particular, we're able to get diffusion language models that can have upwards of 1,000 tokens per second. And we can do it on NVIDIA GPUs. And these kind of speeds, you would typically only ever see using specialized AI inference chips. The model works really, really well for code completion. It was benchmarked by Copilot Arena for autocomplete. This is an academic benchmark where humans are able to evaluate the quality of different kinds of code generative models. It's like an ELO score kind of thing where developers see 2 completions and then they vote which one they like more. And turns out that completions obtained with a diffusion language model that can use context to the left and to the right not only are the fastest, you can get them very, very quickly, but they also rank number one, tied with a few other models for quality. So really high quality completions in very, very quickly. And so, yeah, this is kind of like a summary. I see that I'm out of time, but I hope I convince you that although so far most generative models for discrete spaces have been autoregressive, there are ways to get diffusion models to work on discrete spaces like text and code. This is very exciting because it enables much faster generative models. There are other benefits like controllable generation, the fact that you can use context to the left and to the right, which are pretty exciting as you think about different applications of these models. And yeah, it's no longer the case that the quality doesn't match what you can get with autoregressive models. We've shown in the academic papers that it matches autoregressive models at relatively small scales. And even if when scaled up, the trend continues, and these models are actually very, very competitive with some of the best models out there. And they're starting to challenge the autoregressive dominance that we're seeing today. And that has been true for a while. And so I'm pretty excited about this direction, and wouldn't be surprised if in the future we're going to see diffusion models as being the unified paradigm for generative models, including single kind of generative model that can handle all the modalities that is going to be based on diffusion. I think that's entirely possible. These models seem to be better in many different ways, and so yeah, I wouldn't be surprised if that's going to happen. And I'm very excited about keep pushing the frontier of what's possible in that space. And yeah, I think I'm out of time, so I'll maybe stop sharing and I'm happy to take questions.